Okay, now I'm very pleased to introduce our speaker today, Martha Razzle. And just a little information about her talk tonight. Prediction of the next event is important for organizations to improve and optimize their system process to achieve organizational goals. Existing predictive models are limited since they use discovery algorithms that might not be able to conserve the sequences of events as reported in the log. Discovery algorithms alter the sequence of events in two ways. Either the algorithms generate an additional sequence of events not found in event logs or remove the order of events. Since prediction relies on these process algorithms, the prediction model can suffer and produce underperforming results. Models that do not use discovery algorithms, such as deep learning models, ignore completely the sequence of events. Oopsies. To overcome these limitations, we propose a new algorithm called AXDP, Adjacency Matrix Deep Learning Prediction Model. AXDP predicts the next event of a process using graph theory techniques, specifically adjacency matrices, and predicts the power of deep learning models. AXDP has a major advantage in that the sequence of events is conserved and resulting in better prediction of the next event. When testing AXDP on 8 publicly available datasets, AXDP outperforms what we believe to be the most recent and best predictive models that exist for the prediction of the next event for 6 of the 8 datasets. Okay, and then on to our speaker, Martha Razzle.
Thank you. What a pleasure. What a beautiful day, right? Cold. So let me see if the pointer works. Or would I have to tell you about the slides? Okay, that's fine. So my name is Martha. I am a very interesting person because not only do I get involved and dive into mathematics, engineering, all of this machine learning, deep learning, I'm also a businesswoman. So I run several businesses, one of them being my favorite. I'm the CEO of Weddle's Pallets. It's a pallet company. I'm also an author of a book series called Business Diva. Along with that, I'm a business consultant. And I'm still finishing my doctorate at UIC, and this is one of my publications, and it was a theoretical piece that was accepted by the IEEE Access, which is a big deal. So I'm excited to share this work with all of you. So let's go to the next slide. All right, so what is the problem? So, there's a lot of prediction models out there, but my focus was really on analyzing process mining models. So what do these do? The essence of a process mining is that you take data in form of an event log. I will show you shortly how an event log looks so you can visualize. But basically, you're given this data set in event log form, and then you create a graphical representation. These graphical representations have names called PetriNet and reachability graphs. So you can just think in graph theory, the nodes and the edges. So these nodes usually represent the activities, the events, and then the edges represent some connection between those events. Okay, so just so you get an idea. So what is the existing issue with process mining and the modeling methods is that they tend to overgeneralize. So there's traces. So they don't conserve the information. And that's why there was a need for me to develop something that's able to conserve the information of events and also keeping in regards the time of data, when data happened, because at the end of the day, if you think about it, how do we learn best? By looking at the past, right? And in order to look at the past, we need to look at those different timestamps. So that is the power of process mining. Another type of modeling is deep learning models. The thing with deep learning models, if you know this, is that they use activation functions, and they're so complex inside of these activation functions. It's hard to explain it. It's not like linear, like when I'm talking multiple linear regression or linear regression. You have this slope, and you can easily explain it. Multiple linear regression, you have a bunch of variables, and you can easily explain those, right? In deep learning, you can't really much explain. So the essence is here, what I'm trying to do is develop a model that takes event and conserves those events for every trace. So let's go to the next slide. So this is some of the existing work that's used for prediction. The goal here is to predict the next event. when you're thinking the next event, this can be in anything. I mean, just think about automation when you're designing a vehicle. How to predict when there's going to be the next flaw, when the machine is not going to work. If a company costs them $1 million, let's say a few $1,000s, and this happens a lot, you want to avoid that, right? That's why prediction in that scenario is important. In a medical setting, let's say you're looking at cardiac arrest patients, you want to reduce the number of patients that die due to cardiac arrest. So you would like to predict when that is going to happen to avoid that. It doesn't always have to be a negative outcome, but this is the essence of what we mean with predicting the next event. So these are some of the existing work, the best out there. I mean, I read tons of publications. So you have LSTM, long short-term memory, deep learning models. They use one-hot encoding and then transform these activities, these event logs, into vectors. Then you have RRN neural networks. You have embeddings and LSTMs, and the best one. So these are different methods. Okay, they use deep learning models. The best one existing so far was Meetup, this last one right here, and they use a multi-input approach. Basically what they do is they take everything. They take an event log, they take the resource, they take the frequency, they take the activity, they take everything into a deep learning model, and they use a coding function before they put it into this deep learning model for prediction. So point is that there's already these existing models. You can look them up. They are in the paper if you look up the paper, and you can read them deeply yourself. But this is what I did. Let's go to the next slide. So there's these 8 data sets. All of these papers use these 8 data sets. They're commonly used as a benchmark to see how models perform when you're comparing with different modeling methods. I mean, for example, B12, this is an application process. So when you're applying, it's an application process. You have all these data sets, it's 8 of them. So these are the number of traces and events and the number of activities. And I will show you what this means. Let's go to the next slide. Okay, so this is an event log. This is what I was talking about. And this is how process mining works. It takes data in this form. So you have an event like a patient, that's what is called a trace. Patient 1 is one trace. Patient 2 refers to a trace 2. And notice that there's a timestamp associated for every description, in this case being the activity. So instead of calling it description, I should really have called that event. So for patient 1, which is my trace 1, there is a timestamp associated with that activity. So to put it in context, if you go to a doctor, you check in, that is, you are trace 1, you represent trace 1 as that patient. So your first activity is you register. Then you're going into the room. Then they do your vitals. That's another event. Then another event will be discharge. Okay, so we got that idea? So this is what an event logs, and this is the form of the data, and this is how it looks in context. All right, let's go to the next slide. So what was my goal? My goal was to create a robust and accurate framework for predicting the next event in a system. I focus mainly on medical data, but this also works in business because that's my goal at some point, is to use it in my business. And in any existing organizations, you can think non-for-profit, you can think profit, you can think anything, even in how they run this organization. Right now, we have probably 10 people here. What is the probability that the next date, the next month will be another 10? Or when would be 20? You can use this if you collect data in event log form. All right, so what is the approach? My approach, I did a lot of research, and I also I did mathematics, and one of the things that came up was graph theory. You see how they use adjacency matrix graph theory? It was a combination of graph theory and linear algebra. So I combined the idea of adjacency matrix to plot these, not to plot, but to set these events so I conserve the sequence of events. And I'll show you how I did that. So why adjacency matrix? There's no added or lost information like we saw in process mining with these Petri nets and reachability graphs. Adjacency matrix have been used in the past, like their eigenvalues, maximum eigenvalues. These features, they still don't know why they work, okay? But these features have been important in determining cognitive disabilities and making understanding complex problems in the medical field. That is where this idea even came from. Why adjacency matrix? It just shown medically that it helps a lot, the different components of adjacency matrix. I'm like, let me give it a try. And it worked. This came from this idea. Let's go to the next slide. All right, so what are the advantages? Think about this. The advantage here is conserving the sequence of events. For every trace, if you think patient, I am not removing any of the events, nor I'm adding them, nor I'm changing it. I am conserving them by using this adjacency matrix. So let's see how the algorithm works. Okay, so phase one, you're given an event log here, represented by this L, and you have a trace. You remember how you saw that trace? Okay, so every trace, you have different events. So what we're doing first is creating a tuple of those events. So you have A, B, C, D, E events. Okay, just think about that, A, B, C, D. So I would take A and B, and I'll create a tuple. Then I have the next event, B and C, then I'll create that tuple. Then I have C and D, I'll create that tuple. So that's the first thing. That's referring to my first consecutive events. Then I'm gonna create the second consecutive events, which is A and C, and then C and E, okay? So now I'm gonna create a third consecutive event. I'm just doing first and second, but I also do the same with third. A, and then D, and then D, and you get the idea of what I mean. So then I create these different tuples for first, second, and third consecutive event. And I do that for every trace. And every trace has their event. Do you want me to go back to just show this? Or is anyone lost here? Yeah, let's go back to that event log. Here, let me put it from here. Okay, so let's assume this event register A, B, C, D, E, F, G, H, okay? I'm gonna rephrase them. So first consecutive tuple will be these two. Second consecutive will be this registration and check vitals. And then the third one will be registration and physician care. You got that? No, I will put them together, so A and B. It's a different terminology. I just combine them here. No, it won't be a tuple in Python. For me, it just refers that I put them together. I concatenate them. Is that the word? Pair values, there you go, pair values. I make pair values. So here I'm forming a list. I'm making a list, A, B. Okay, but I just call it tuple here because I'm making two. No, I'm not using that, so no. Okay, basically what I'm doing is listing them. I didn't bring the source codes, but I would have showed you. Okay, but I can share the source code. When I'm done, I can show it to you. I use Python. No, it's not related to Python language. No, it's related to math language. Okay, let's go. But at least you got the idea what I mean with these consecutive events and second consecutive and third consecutive events. I just want you to visualize it, what I mean. Okay, so for every trace, I do this. So let's go to the next one. So that's step one. For every trace, this is how I combine these different consecutive events. Okay, so now I have A, B, A, C, A, D. So I create an adjacency list. And from the adjacency list, I create my adjacency matrices. So now I have an adjacency matrix for first consecutive events. Then I have an adjacency matrix for the second consecutive events. And then I have a adjacency matrix for the third consecutive events. So how does that work? So if we were to put all these events in adjacency matrix, then you have A, B, C, D here on the columns, and on the rows, A, B, C, D. So if you go A to B, then I will assign you a 1. And if you don't have a node or there's not an existing tuple, then you're a 0. If you are AB and then BA, AB, BA, then I will assign a 2. Okay? It would be nicer if I had a board to write these things, but do you get me? Okay, so we create this adjacency matrix. Let's go to the next one. All right, so for every trace, now we're gonna do this. So now we have our first matrix. We're just gonna reshape it because we need to, the objective is to use this as an input for the deep learning model, for the neural network. Okay, so for first consecutive events, there are m number of traces and n number of events. So it'll be n by n squared matrix here. Now we reshape the first matrix. So what is going on is m represents the number of traces. Remember, that will be the number of patients, and n is a number of events. So we're gonna square that because the matrix was an n by n, okay? All right, so that's my first entry for my AXDP algorithm. Let's go to the next one. So now for the other ones, for the second and third consecutive events, what I'm going to do is I'm going to calculate the eigenvalue, and I'm going to take the maximum eigenvalue as inputs. So I'll take eigenmax 2 and eigenmax 3, input 2 and input 3. And this keeps some of the information of the relationship of these events in the second and third order. All right, let's go to the next one. Okay, so now we're going to calculate the frequency of every event for every trace. So how many A's happen? How many registrations happen? I mean, in medical, in reality, it will be only one registration, but how many events for every patient, the frequency of them happen? So that'll be my input 4 into this deep learning model. All right, let's go to the next slide. So this is the general framework. You have your data in event log form. You remember how that looked. I take my reshaped first consecutive adjacency matrix that we reshaped into an n by n squared. Then I take the max eigenvalue representing the second and third consecutive events. And then I take the frequency of those events, and then I feed them into a deep learning model. So they go into this neural network. That's a whole different thing that I can spend a whole day explaining. And then we predict the next event. We can go to the next slide now. So these were the results. Note that we compared with I compared in this paper with 6 different models, but for the reference of this picture, I just compared directly with Meetup, which I said that was the best related to all the other research. So just for your point of reference for like quicker and one easy graph, I only compare here directly with Meetup. But in the actual paper, I compared with 6 other different predictive models. So what did we find out is that AXDP works. We still, I don't think anyone will be able to answer this right now. Why does the maximum eigenvalue work? No one will really be able to answer that yet, but it works. Why does the adjacency matrix works? I can answer that because we're conserving the information. Makes sense. If you are being fed information and being taught, Petri nets, process mining sometimes is like the telephone thing. It can give you not the whole story, but adjacency matrix conserves the sequence of events. So it gives you everything. So if you're learning, you have the whole information. Now it depends on your interpretation. But if you only get a snap of the information or information that's not the entirety of it, then you're not gonna really learn or interpret the correctness, you get me? In this case, you're not gonna make the correct prediction. So that is why the adjacency matrix is stronger than all of these LSTMs, RNNs, convolution neural networks, because of the essence of the conserving of the sequence of events. Okay, let's go to the next slide. Let me see how I'm doing in time. Okay. So these were the results for 6 of the data sets. Remember, we have 8 different publicly available data sets. The AUC score was the highest compared to all the baseline models. So 6 out of 8. For 19, 16, and 13, so these are the names that I use in the citations. 19 is Meetup, 16 is an LSTM, and 13, that's tax. 13 is LSTM, and 16 was, it was a deep learning model, have a higher AUC score than AXDP for this particular data set. I still don't know why. And that is what I want to figure out. Why didn't my model perform good on BP12 complete? And then AXDP has the lowest compared to all models on B17 offer. But in general, we can make an argument that AXDP is the better model because 75% of the time it outperforms the state of the art baseline models. I will love more data because I keep testing it, but it did work too on a medical data that I use for paralytic alus. I already published one paper, but I can publish this, but they didn't let me using my method. They want me to create a new method. So let's do it. They're like, that's too easy, Martha. That's experimental. So I need to create a new theoretical work. All right, let's go to the next one. So what are the limitations? And maybe someone can figure this out. If you want an open problem, one of the biggest problems in literature, I don't think anyone has really figured it out, is when you have data and it's not balanced. So for example, if you have dead and alive patients, you mostly have less dead patients than alive, right? Hopefully. That's just an example. And in a company, you have less errors than you have successful cars being built. But in that class imbalance, how do you deal with that? There's a lot of different works that have been developed, but there's no like, okay, this is the formula, the magic formula. So that's something in the future I will actually like to keep working on, how to deal with class imbalance. And I know I'm not 100% sure, but I'm sure that in these two data sets that I explained before, B12W complete and B17, that probably explains why the model didn't perform that well, because there's probably a lot of class imbalance. Because in some of these data, you were dealing with 12 different classes. So that means like 12 different events that you could have predicted A, B, C, D, E, F, G, H, I, do you mean? Instead of 0 to 1. So imagine having a class imbalance in 0 to 1 and also having a huge class imbalance in 12 different events. One event can have just one occurrence. But for example, the 12th event can have 20,000 occurrences. Do you get me? Where there's a problem there. Okay, so I would like to test other neural networks. For this paper, I just did ReLU. I don't know if you heard ReLU is the commonly used activation function in neural networks. I actually developed one, and I hope that paper publishes. No one can know yet, but maybe implementing different activation functions that we can develop. So that's something I'm working on. How to improve existing activation functions so they can work for this class imbalance issue. I don't know. We'll get there. Another thing is convolution neural networks. I'll probably start there before I create one, because convolution neural networks, there's already existing Python code for it. Let me see if I'm forgetting anything. No, that's it. Any questions for me? Oh, this is a conclusion. I kicked their butts, basically. Yes. Um, the reason they use AUC versus, let's say, accuracy score, they have their ups and they have their goods and their bads, but AUC has been used for imbalanced classes best. So if you're dealing with imbalanced classes, then go with an AUC score. And of course, because I'm comparing with existing literature, I need to use a common baseline. So those are the main two reasons. If I'm talking about accuracy and they're talking about AUC score, like we're not talking about the same thing. It's those two reasons. But AUC score, I will go with AUC score over accuracy, especially with dealing with such a broad range of data with class imbalance. what you can do for those instances is add a weight. Within Python, I didn't do it for these experiments, but there is a code that you can add a weight. When you are predicting within the neural network, you can weight one class. For I didn't try it here, but would it? It probably will, but I had to be more strategic. And the thing is that now this will become a whole different paper. It will become a paper of like, how do you stratify how you put weight on class imbalance? Hey, and maybe that solves a class imbalance if there's a system or an algorithm for stratifying how to add weights. Oh my God, what if this is the start? This is crazy. I know. I'm going to go back to my house in the plane because I'm going to a plane right now. But for you, and this is what I noticed in time series, there is one flaw with time series. It only looks at time. There is other factors involved. So maybe creating the time series and adding more variables, like a market index or something. I don't know because I'm not an expert in the area. So I don't know the answer why it really worked. The why I used it because my research was on the basis of medical field. So in my department, we do research on predicting different diseases, different like cardiac arrest, diabetes, PI. So I dived into adjacency matrix, and then I found a lot of publications that use maximum eigenvalue to determine, for example, the different patterns in our brain. Like if you look into this eigenmax value in medical predictions, you will be like, oh my God, this is incredible. So when I saw that, I'm like, there is something behind the eigenmax value. We can, hmm? And it forms, and it is a characteristic of that adjacency matrix per se, right? Because it's a linear function of these other components that make that adjacency matrix. So that's a smaller set of the big matrix. So this is another reason I also used it because I can use the big matrix. Imagine I have 19 events, then you're 19 by 19, so it's 19 squared. That is huge. But now if I take the eigenmax value is one component rather than this large. Yes, there you go. And next time I'm going to answer exactly like that. Yes, I use Python. No, let me see. Let me see what time I'm at. I can't connect my computer here, right? There is a port for Samsung. I have a Samsung. Yes, send it on LinkedIn and I'll go through my computer. Hey, we should torture the people online. Well, you're not gonna see the source codes because you didn't show up in person. I'm just kidding. Right, I'll be quick because I gotta run. Python. I gotta show it to you. You can see the beauty. I'm just gonna use mine. Oh, it's free? You don't, there's no password? Oh, perfect.
Recording in progress.